Let's proceed to the next common measure of variability, which is variance. So, what is variance? Variance is the measure of dispersion, meaning it is the measure of how far a set of numbers are spread out from their average value. So, it tells how much students' performance varies around the class average. So, we have different formulas used for calculating variance depending on whether you have the data from a whole population or a sample. These are the sample variance and population variance. So for sample variance, we have the summation of the square of the difference of x minus x all over n minus 1. Or in simpler form, this is the summation of the square of the division divided by n minus 1. So for population variance, we have the sigma square is equal to the summation of the square of x minus capital N. Where s squared and sigma squared is the variance, x is the individual value, x bar and u is the total number of value, and capital N is the total number of value. So, how do we interpret variance? High variance means that the data points are more spread out from the mean and from each other. An unbiased estimate in statistic is one that doesn't consistently give you either high values or low values. It has no systematic bias. Just like for standard deviation, there is a different formulas for population and sample variance. But while there is no unbiased estimate for standard deviation, there is one for sample variance. If the sample variance formula use the sample n, the sample variance would be biased towards lower numbers than expected. Eh, Reducing the sample n to n minus 1 makes the variance artificially higher. In this case, bias is not only lowered but totally removed. The sample variance formula gives completely unbiased estimates of variance. Let's have the example. In the beginning, we have mentioned that these are the top scorer of English Tastic, meaning this is not the totality of the scores, just a sample. So, we're going to use the formula for the sample variance, and that is again s squared is equal to the summation of the square of the difference of x minus x bar all over. We already rated our x value and we have also computed for the value of our x bar. Now, for our x minus x bar or the deviation, we just have to minus 50 minus 28 is equal to 22, and then we're going to square the value of 22. So 22 squared is equal to 484. 36 minus 28 is equal to 8. So 8 squared is equal to 64. 24 minus 28 is equal to negative 4. Negative 4 squared is equal to 16. 20 minus 28 is equal to negative 8. So negative 8 squared is equal to 64. 10 minus 28 is equal to negative 18. Negative 18 squared is equal to 324. Now let's get the sum of the division. We have 22 plus 8 is equal to 30. 30 plus negative 4 is equal to 26. 26 plus negative 8 is equal to 18. 18 plus negative 18 is equal to 0. Remember, the sum of the deviation of values from the mean is always 0. Now let's get the sum of the square of the deviation. 484 plus 64 is equal to 548. 548 plus 16 is equal to 564, plus 64 is equal to 628, plus 324 is equal to 952. We're going to substitute this value in our numerator, and again our n is equal to 5. So 5 minus 1 for the denominator. So 952 divided 4 is equal to 238. And that is our variance. Now let's Last but not the least measures of variability is the standard deviation. So what is standard deviation? Standard deviation is the most useful and most frequently used measure of dispersion, expressed in the same units as the data or variance. A large standard deviation indicates that observation or data points are far from the mean, and small standard deviation indicates that they are clustered closely around the mean. Zero standard deviation indicates no variation and all the values of the variable or the dataset are identical. So, standard deviation is the square root of variance, placing the value back into the same unit as the scores. It measures on average how far each value in a data set is from the mean. And we also have two formula for standard deviation, the sample standard deviation and the population standard deviation. So we have two formulas for standard deviation. The first is samples. So if you have the data from a sample, you use the sample standard deviation formula, which is the square root of the sample variance. And for the population standard deviation, if you have the data from the entire population, you may use the population standard deviation, which is the square root of the population variance. So just the square root of population variance, and also for the sample variance, just the square root of sample variance, where S and sigma is the standard deviation, X is the individual value, X bar and U is the sample mean, and capital N is the total number of value. How do we interpret the standard deviation? High standard deviation means that the data point are more spread out from the mean, more spread out. So, why use n minus 1 for sample standard deviation? Samples are used to make statistical inferences about the population that they came from. So, when you have population data, you can get an exact value for population standard deviation. Since you collect data from every population member, the standard deviation reflects the precise amount of variability in your distribution, the population. But when you use sample data, your sample standard deviation is always used as an estimate of the population, estimate from the standard deviation. Just estimate. Using n in this formula tends to give you a biased estimate that consistently under reducing the sample n to n minus 1 makes the standard deviation artificially large, giving you a conservative estimate of variability. While this is not an unbiased estimate, it is a less biased estimate of standard deviation. It is better to overestimate rather than underestimate variability in samples. The difference between biased and conservative estimate of standard deviation gets much smaller when you have a large sample size. Let's proceed to the example of the standard deviation. And this portion here, the one inside the square root, is the formula of the variance. And we have computed its value earlier, and that is 238. To solve for the standard deviation, we just have to get the square root. So the square root here and this exponent 2 here will be cancelled out. So the square root of 238 is equal to 15.43. Recall that our mean is 28. This means that the scores are clustered within 15.4 around the mean. That is between 12.6 and 43.4. So how do we get the 12.6? We get that by subtracting the mean, and our standard deviation. So 28 minus 15.43 is equal to 12.6. And for 43.4 is we get that by adding our mean and our standard. So 15.43 plus 28 is equal to 43.4. So, what is the best measure of variability? The measure of variability depends on your level of measurement and distribution. The level of measurement for the data measured at an ordinal level, the range and interquartile range are the only appropriate measure of variability. For more complex interval and ratio levels, the standard deviation and variance are also applicable. For the distribution, normal distributions, all measures can be used. The standard deviation and variance are preferred because they take your whole data set into account, but this is easily influenced by outliers. Measures of variability plays an important role in understanding students' performance beyond simply looking at average score. By examining how widely scores are spread, teachers gain a valuable insight into the consistency of learning, the presence of learning gaps, and the overall effectiveness of instruction. Tools such as the range, interquartile range, average deviation, variance, and standard deviation help reveal whether students share similar levels of mastery or if significant differences exist within the class. Low variability suggests that students perform consistently and likely understood the lesson similarly, while high variability signals diverse level of comprehension that may require targeted interventions or differentiated instruction. Ultimately, these measures support more informed decision making, enabling teachers to adjust teaching strategies, address individual needs, and create more effective learning environments. And we hope that you learned something from this lesson or discussion. And that would be all. Thank you.